Well then, as we're already live on YouTube and Dragos claims this is the MPC podcast, fair enough. Yeah, so today it's our great pleasure here at TPMPC to have Xiao Wang give a extended talk. So Xiao got his PhD from Maryland under supervision of John Katz and is now an assistant professor at Northwestern. And if in the past 6-7 years you have ever looked at any protocols for efficient 2PC, MPC, ORM, PSI, zero knowledge, and so on and so forth. So basically, if you looked at any of these papers, there's a very good chance that Xiao was involved in this. So that's why I'm very happy to see his talk now about his most recent results. So Xiao, take it away.
Thanks, Carson, for the introduction. Let me start sharing my screen. It looks good. Okay. Yes. Let me move. So again, I'm Xiao. So today I'm going to talk about concretely secure multi-party computation. It consists of two works, and both of these works are co-authored with Chun, Zhang, my student Chen Kai and Yu from different universities. Okay. So at the very beginning, I'm not going to talk again about exactly what is MPC, but let me first just give a high-level idea to categorize the MPC research in the field. So we can view it as like a stack with 4 layers. Okay. And the top layer, we have all different kind of applications that we are building, like privacy preserving machine learning, anonymous communication, auction, and all different kind of stuff. So these are applications facing to the users. And all these applications are usually built on different kind of protocols or key building blocks. These building blocks can be coupled circuit, WBS transfer, all different kind of triples, all different kind of OLE, VOLE, and all more building blocks. And these building blocks are in turn built with some kind of assumption or trusted setup. Okay. So for example, we might need some kind of assumption, computational assumptions like DDH, LWE, and all different kind of stuff, all trusted setups like random oracle, CRS, or stuff like that, and all probably we also need very likely we need some kind of PRF, runway function, or different kind of symmetric primitives. Okay, and but up to now everything is more on paper, right? When we say random oracle, it's just a trusted setup, and in practice we need to implement them. And when we implement them, we need to choose all different kind of instantiations. For example, for DDH, we need to choose the group. For random oracle, we might, for example, we can choose instantiate random oracle using SHA-256 or SHA-3. And for example, for PRF, we can instantiate using AES and all different kind of choice of instantiation. Okay, so most proofs, I would say almost all proofs that we have been writing and all the proofs that we have been seeing, they mostly cover the first 3 layers. Okay, so for example, we have applications, they might be built on protocols, and if the protocol is secure, then the application is secure. And that's also the case from the assumption layer to the protocol layer. However, when we get to the implementation instantiation, things get actually very dangerous and messy. It's first, many of them are not provable. However, but when we implement them, we use all different kind of optimizations or fork laws, and these fork laws are usually not proven secure. So over here, this is essentially the kind of the danger zone that can cause different kind of problems in the proofs and in the implementation. And as we know, and as long as one of the layer has some kind of problem, the whole kind of security breaks down. And so in this talk, we mostly focus on the bottom 2 layers. Okay. So for the red part, we want to find suitable hash function abstractions for MPC. Okay, what kind of hash function abstraction is suitable for us to use in MPC applications and the protocols? And then we also want to and also the bottom layer. So essentially, what's the most efficient way to kind of reasonably instantiate these hash function abstractions that we will use? Okay, so kind of a kind of an outline. So we will first talk about the random permutation model. And then we talk about the ideal cipher model, and then we talk about what we should do actually in practice. And then for the first two part, the first part corresponds to our Oakland paper published in Oakland this year. And the second part corresponds to our paper that is accepted to crypto this year recently. So for each part, I will talk about what kind of abstraction is good, and then we'll talk about what kind of instantiation is kind of reasonable with some kind of like a rarely known, rarely accepted instantiation. And then finally, we'll talk about what we should do in practice. Okay. Well, but before I want to talk into the detail, one question is that why I want to focus on hash functions, right? There are so many different kind of stuff. Why I just want to do the hash functions? Well, this is mostly because hash functions are actually very, very widely used in MPC protocols. For example, in many cases we model hash function as a random oracle and just use random oracle in various part of the protocol. And in many cases, including say OT extension and Goblin and many other examples, we usually just use this hash function to hash a short string. Okay, so this is very different from the most common use of a collision-resistant hash function, where we usually hash a big chunk of data. But in many MPC protocols, we only hash short strings. Well, I mean, since we actually in most cases a random oracle is sufficient, a natural question is that why not just use a SHA-3 and we model it as a random oracle, then we essentially solve all the problems. That's actually true, except that the performance is actually a big issue. Especially here, when we just want to hash short strings. So here is a kind of a benchmark that we did last year. So essentially, so in the table we have different kind of primitives, including SHA-3, SHA-256, AES plus case scheduling. It should be case scheduling plus AES because we first do case scheduling, and then this XRP. I will talk about XRP. What does it mean by XRP later, and also the fixed key AES. Okay, so on the y-axis we have different batch size. So essentially, if we want to do one operation, or we know that actually we can do operations in batches. Okay. So as you can see, if we have a lot higher batch, then actually the performance is better. So this number is the number of CPU cycles that we need to compute one instance of the operation over here. So for AES, it's when we have a large enough batch, then essentially it's 10 cycles, and it's as expected, because with AES and I, we can do one round of AES encryption using one cycle. So AES has 10 rounds, so it's 10 cycles. It's the implementation match what we expect. So XRP is a recent construction that actually is indifferentiable from random oracle. Okay, so this is probably indifferentiable from random oracle. It uses two. It essentially is XRP actually stands for XOR permutation. So it takes two random permutation and then XOR the result. And then they can actually show that if the two random permutations are independent, then actually the result is indifferentiable from random oracle. So we can, for example, if we assume that the fixed key, if we model a fixed key ES as random permutations, then essentially the XRP can be implemented in this way, with fairly good with reasonable it's a reasonable instantiation. And in this way, where the performance is about is 22 cycles per operation. This also meets the expectation. Well, I mean, right? It's 2 AES would take 20 cycles, and there's some kind of overhead. So this also good. Okay. And then we have AES plus key scheduling. Okay, so this is still reasonable. So here I already this number already incorporated the optimization done by Goron et al. Forgive me if my pronunciation of the last name is wrong. So essentially over here they have optimizations where they can optimize the key scheduling part using AES and I. I'm going to talk about it a little bit more afterwards. So, but here you just need to understand that, okay, so it's actually also reasonably fast. But when we go to the SHA-LAN, the things becomes much slower. Okay, for example, for SHA-256, it requires about 600 cycles to hash short strings, 128. Why that's the case? Well, SHA, all these SHA hash functions are designed to hash large chunks. For example, for SHA-256, they actually take 512-bit chunks as input. So like a hashing short strings is of course not going to be efficient. I mean, also like they have much more round than a fixed KES. Even if we use actually SHA, for example, SHA-NI, it can only be accelerated by like 3 times, but no more than 3 times. So you can see actually that's still going to give us like roughly a 20 times gap between SHA-256 and the fixed KES. So the gap is still large. And for SHA-3, it's even higher because it's I don't think there's any kind of hardware native instruction support for SHA-3 at this moment. SHA-3 is actually, I think SHA-3 is faster than SHA-256 for large chunk of data, but for small chunks, I don't think it's actually faster. Yeah. Okay. So we can see actually there is a very big there is a very strong motivation for us to use like AES based construction for hash functions that is being used we use in MPC protocols instead of use SHA. But how to do it securely and you know, like kind of a nice way is actually unclear. That's like the part that we want to focus on here. Okay. So let's first talk about the random permutation model. Okay. Let me first give a little bit background on exactly like what does it mean by random permutation model. Like I believe like probably like many of you like don't know much about the like symmetric key as I was like 2 years ago. So we can go into we can get some background first. So essentially, we assume that actually we have a access. Everybody has access to a fixed permutation. Okay. So this permutation takes a like 128 like a n-bit string as input and output an n-bit string. And this permutation like is a kind of a fixed permutation. Okay, so when we say the random permutation model, we just assume that this permutation is a random permutation. Essentially, this permutation is kind of it's kind of a trusted setup. It's like sampled from all possible permutations in this manner, like randomly at the onset of the protocol. Okay, so it's from this sense, it's actually similar to the random oracle model, but it's like it's kind of I would say it's kind of restricted in terms of the entropy, because the entropy in this pi is kind of limited, and like the format is also kind of limited. Yeah. And then for the attacker like everybody actually have oracle access to the random permutation or the inverse of the random permutation. So we can do forward and backward access to the permutation. Okay, so in practice, for example, we can instantiate random permutation using AES, where the key is a fixed and a public key. For example, like we can just fix we can just model AES with a fixed key as a random permutation, and this is a fairly good instantiation, I would say. I think the best known attack that distinguish a fixed KES with a random permutation can only attack a 7-round AES. So we still have like a 3-round margin in that sense. So it's kind of a pretty good instantiation, like a instantiation in this sense. However, how to get more from random permutation is still not clear. Okay. So the use of random permutation, as far as I know, in the MPC world, was originally proposed advocated by the Just Garbo paper, published in Oakland 7 years ago. Okay, so it shows that for the first time actually gobbling can be so fast, so much faster than people thought before. So it's a very nice paper. And then, however, the paper actually proved the whole gobbling scheme to be secure in the random permutation model. Okay, so they just show, okay, so if you do this, then the protocol is secure in the random permutation model. And then people started to borrow the essence of the Just Garbo protocol into many other protocols. For example, in OT extension, in all different kind of triple generation and gobbling schemes, we borrow how they use fixed KES in these schemes in some way that we thought it should be fine. Yeah. What does it mean exactly? Let me give a overview on what's the picture. Okay. So remind that we have 3 layers. Okay, protocols, assumption, trusted setup, and the implementation instantiation. Okay. So here, let me just focus on 4 set of schemes. Okay. Passive OT extension, active OT extension, Just Garbo, and HalfGate. Okay. In the middle ground, so we first have a correlation robust hash function. Okay. So this, as far as I know, the first paper that I thought this concept to be mentioned was the ICANN OT extension paper, where they actually proved that actually the OT extension is secure in the correlation robust, with the correlation robust hash function. Okay. So actually, the passive OT extension is indeed secure with the popularly defined correlation robustness, but there are many variants of correlation robustness. And for the active OT extension, the proof is kind of I would say problematic, depending on what kind of correlation robustness that we actually use. Whether we have a tweak with it is a particularly important problem, due to some kind of descriptions of the protocols that we use, and this would be clear later on. Okay, and in terms of how to instantiate this correlation robust hash function, the best probably way that we know is actually random oracle. Although, and we know that it's actually much weaker than random oracle. For example, correlation robustness is actually a standard. It's not a it's something that can be instantiated, but the random oracle can never be instantiated in some way. So it's definitely kind of weaker than the random oracle, but we don't actually have any proof of provable construction of correlation robust hash function beyond actually just beyond just using random oracle. Okay. And on the other hand, we know, as I just mentioned, that Scarborough is proven secure in the random permutation model. Okay. And in terms of HalfGate, so HalfGate is actually proven secure in some so-called it's a relaxed circular correlation robustness. So this part is solid. However, that definition of circular correlation robustness is actually cannot be proven secure in the random permutation model. So actually, actually in our paper, we actually showed that this concept is actually too strong in the sense that it will never be proven secure, and any construction that satisfies this notion cannot be proven secure in the random permutation model with a polynomial bound. So this part is somewhat problematic. Okay, and in the end, Xiao, random oracle can be should be instantiated with, say, Xiao-256, and random permutation can be instantiated with fixed KES. So this is what's on paper. Okay, so this is what's probably known and what we are supposed to do in practice. However, in practice, what we do is that, okay, so we are going to just instantiate everything with fixed KES because of the high performance it gives. For the correlation robustness, we instantiate with a fixed KES. For the active OT extension, we actually also instantiate with a fixed KES. And for this, we also just essentially we kind of use our intuition, just use fixed KES for essentially everything. As long as it looks like a hash function, we use something that looks that seems to be fine. Okay. Yeah. Okay. So it's definitely not something that we want to it's definitely something that we want to fix, and so let's try to fix it. Okay. So let me first give a high-level idea about the result of the fix. So essentially, we show that actually the active OT extension can be proven secure in the tweakable correlation robustness hash function. Okay. So if we have an explicit tweak, and if the definition is correct, then actually the proof goes fine. And then we show that actually the HalfGate is secure, although it's not secure in the relaxed circular correlation. So we can actually directly prove the security of HalfGate in this so-called circular correlation robustness by modifying the scheme a little bit. Okay. And then we show that so all this concept can be proven secure in the random permutation model. So there's so this scheme, all these hash functions can be proven secure in the random permutation model. And the random permutation can, of course, be instantiated with, for example, fixed KES. Okay. So let me. So now it's probably a good place for me to introduce a little bit more about correlation robustness. Okay. So essentially, correlation robustness can be viewed as a way to construct PRF. That's how I view it. Okay. So let's say if we said that a function is correlation robust, essentially it means that we can construct a pseudo-random function using this way. Okay. So if we have a PRF, we can construct the PRF by just XOR the key and the input and hash it, and the result and this should be a pseudo-random function. If this is true, then H is a correlation robust hash function. This is just like this is the one way to view correlation robust hash function. Okay. So this is actually like a stronger version than the version that it was originally defined by Xiao et al. It's so this version is stronger in the sense that the original version that was proposed in Xiao et al. Is kind of essentially the same, except that they are saying that H is correlation robust if the PRF is a weak PRF. Okay, it's a weak PRF that essentially means that it's like it's secure as long as X is random. But here we are saying that okay, we don't want that constraint. We want to remove that constraint. Okay. So a slightly stronger version was later proposed in this paper, and essentially over there they are saying that okay, so they want to extend the input length larger than n bit. And also like also show that okay, so as long as the input, as long as K has like limited entropy, then like everything is fine. Okay. So over here, like and then like when we have trigger like a correlation robust, we can also define tweakable correlation robust. Okay. So tweakable correlation robust essentially it's kind of the same like except that we have a tweak. And here we're just saying that okay, so if we have the tweak, then the resulting like PRF, the resulting function defined in a similar way is still a PRF. Okay. So here we can see that okay, so the key difference is that we have a tweak and the tweak is not XORed with the key. Okay. So if I is also XORed with key, then then tweakable correlation robust essentially is a correlation robust with a longer K. Okay. So here like it's not the case. Okay. So I is not XORed with K. Okay. So these are the two concepts. Yeah, as I said, like so over here we don't want to put any restriction on X and I mean, so that it's actually like nicer to use, and also it actually support adaptive queries. Adaptive queries in the sense that the adversary can query this like in the PRF game, like the adversary can query the PRF, get some result, and then submit the next query to the oracle. Because remind that we want to show that this is the PRF, so we need the PRF thing. Okay, so our construction was based on a well-known construction called Matthias, Meyers, and OC's MMO. Okay, I'm just going to use MMO. MMO was like originally proposed as like to be used as a like one-way compression function for the Damgard Merkle Damgard construction. So it looks like this. However, like in our case, because we are just hashing short strings, so like the key there's no kind of HI minus one, like we just hash wets. So this is like kind of deleted. So essentially it's just like, so when we delete this becomes a fixed key. So this E becomes a fixed key encryption. So this is kind of a pi. So we have the message, we permute it, and then we also XOR it with the result, and then we get the hash of the I. So this structure was only proven to be like a collision resistant up to n/2. Since n so for let's say if we aim for AES, n is actually 128. So it's only up to like a 64-bit of security for the one-wayness that we have proven, and no other properties have been proven as far as I know. So here we want to essentially our first result is that okay, we want to show, we actually show that this is indeed a correlation robust hash function. This is a correlation robust, and we also give the concrete bound. So this is the correlation robust for any adversary who make like p queries to the oracle and p queries to the permutation and q queries to the oracle. So for the queries to the permutation can be viewed as like the running time of the adversary. Okay, because adversary can call like these permutations and like in an unlimited way because everybody has access to it. The queries to the oracle is kind of limited in some sense. So we have p queries to the permutation and the q query to the oracle, and then the advantage that the adversary have in distinguishing the PRF with our construct with the random function is going to be roughly like this. Okay, so it's I mean the important part is that it's a multiplication between P and Q. Okay. So for example, for Q queries, Q like in practice actually corresponds to, for example, the circuit size or the number of OTs when we're using the OT extension, stuff like that. I will talk more about the concrete bound later on. So the proof is based on a popular method called the H coefficient method. Okay. And also it turns out that this bound is also tight. Okay. So this bound is tight in the sense that we can actually find a matching attack on this. So this is like this. There's essentially no way to improve the bound. Okay. So let's see how that is possible. Okay. So now, assume that we want to attack this correlation robust hash function. So essentially, we have so we define random function as hash of k XOR is the input x. Oh. This is my New York clock. Okay. And the hash, and if we expand it out, then it equals to this long string. Okay. And we also have public access to pi and pi inverse. And so it means that we can locally compute the hash function on any input we want. Okay. So now, so our goal is that we want to make certain number of oracle access to the random function, and after that we want to have a guess on k. Okay. So if we can guess k correctly with a high probability, then it's not a good idea, right? So it means that we can break the PIF security easily. So what are we going to do? So we will first pick a set of uniform point x1 to xp and compute the hash of them. Okay. So this can be done locally because we can locally compute on pi, so we can locally compute on h. So these p of operations are local computation. And then we pick another set of uniform point s1 to sq and compute the oracle and then send them to the oracle to the to compute f sub k of si and get t of I. So this set are oracle accesses, and then we just try to find whether there's any kind of collision between yi and ti's. Okay, so if there is some yi that equals to some tj, then we just deem that the k has to be xi xor sj. So why that's the case? So we can think about it. Okay, so if this relationship holds, then h hash of xi is going to equal to f of k of si. This should be sj, right? Because xi equals to k xor sj, and the hash of k xor sj is just f k of sj. So if this is true, then then we are definitely going to get it. And on the other hand, if this relationship does not hold, then it's unlikely that that actually these two are going to collide. Okay. So it means that if k actually indeed appears in any kind of the cross term between these two, then there's a high chance that we are going to find it, and the false positive is small. Okay. So essentially, what that means, it means that if we make p local computation and q oracle access, then the probability that we can the probability that k is among one of them is about p times q over all possible case all possible case of k. So that's 2 to the k, 2 to the length of the k, 2 to the n. Okay. So that's where the this kind of quadratic bound comes from. Okay. Because any I and any y and any t gives us a guess of k. So that's where this term comes from. So so as a result, it means that so our actually the prior bound is actually tight up to the constant term. Okay. So one very important fact here is that the attack actually needs the input output pairs and from the oracle. Okay. So we need to know what we send to the oracle, and we need to know what we get from the oracle. Okay, so these two terms we need to get them, and then we need to do some operation to get the attack. So attack highly crucially relies on this this thing. Okay. And then similarly, we can also construct a tickable correlation robust hash function. So so it looks like this, and we can actually prove the security of this, also using H coefficient method. So it's not only a tickable correlation robust, it's also tickable circular correlation robust. So we get both properties within within a single structure. Okay. So in this structure, we actually just need 2 permutation calls because we can just compute pi x once, and then compute the second pi once. So it's actually just need 2 permutation calls. Okay. And this so this structure also suffers from kind of a quadratic bound that we proved similar to the bound that we proved before. And this bound is also tight. It's tight in the sense that there's a matching attack to this construction. Okay, let's look at the result. So with all this result, it essentially means that okay, so now we have the like a correlation robust. We have a circular correlation robust that I didn't mention like that much, but this is essentially a slight modification of the correlation robust scheme with something that I will mention later. And then we have the triggable correlation robust, what we call that TMMO. That is actually fine. That can be used for the active OT extension. And we can see that actually, so the overhead that we impose on top of fixed KES is minimal, and it's not like, and we think that it's probably the best we can do, like given the current techniques. Okay, so essentially, like, so as a kind of a summary, so the first part is that we actually analyzed like many existing protocols and implementations and found that many of them are problematic. We also found some kind of implementation bugs, but like they are like much less minor compared with other like compared with like the abstraction and stuff. And then we have several like we consider several abstractions for the hash functions and what are the abstractions that are actually needed for different kind of protocols. And then finally we showed okay, so actually some kind of so how to use fixed KES in a like a principled way to instantiate all different kind of abstractions. So like so far so good. Okay. So after we are done with this paper, like we thought like okay, so like what should we do next? And then we realized like actually then like so the story is that then like we were involved in the like NIST standardization on the post quantum like primitives. And over there like we were like discussing the concrete security of the signature scheme based on our like CCS paper on like related to MPC in the head. And over there, like we suddenly realized that okay, so we actually need to think about the concrete security of our signature scheme based on our MPC in the head scheme. So we were like analyzing the scheme, and then in like kind of at some part of the discussion, we realized that, okay, so why stop at the signature scheme? It seems that we should also analyze the scheme for other primitives like Gabor circuit and all the stuff that we were working on. That's essentially like where we come down to the concrete security of other schemes that over here. So it's actually that was an interesting discussion. Okay, so I want to like start this part by reminding the attack that I just mentioned a few slides ago. So like so we mentioned attack that actually in the random permutation model that there's an adversary who can actually break the security of the correlation robust with this bound. Okay, so the second term is kind of not too important because in most cases P is going to greater than Q. Okay, so if the adversary is involved in a computation where like adversary needs to make Q queries, the adversary is probably going to be able to make more than P steps of or Q steps of local computation. So usually this is a dominating term. Okay, so what is this term? So this term, so essentially, so P is the running time. Okay, so P is the running time of the adversary. It's like the number of times that adversary can query to the random permutation, and Q is the number of oracles. And when we use artificial protocols, the number of oracle queries usually corresponds to, let's say, circuit size or number of OTs or stuff like this in a protocol. So like to put it in something easier to see, it's like a T over C to the 2 to the n. Okay? So where T is the adversary running time and C is, for example, the circuit size in most cases. Okay. Now, if we write like this, then it might seem like a bit more scary. Okay, why I'm saying that it's a bit more scary because C. So in we have seen like many papers where we Gabor circuit or we compute circuit where the circuit size is as high as 2 to the power 37. I definitely see for example, I think there was a paper on stable marriage where they actually compute a circuit of size 2 to the power 37. Okay. And where they actually use they are Gaboring the underlying Gabor circuit backend only use 80-bit key. Okay, the Gabor circuit backend use 80-bit key, and the circuit size is about 37, 2 to the power 37. What does it mean in terms of T? It means that the provable bound in terms of the adversary like running time is going to be 2 to the power 80 minus 37. Okay, that's probably not a very good bound for us, right? So so this is essentially where things becomes like problematic when we plug in like actual numbers. So typically this kind of bound is called birthday bound, okay, because it's kind of related to the birthday paradox. So it's called birthday bound. So essentially, we want to ask a question: what does it mean? What this kind of birthday bound imply for MPC building blocks, and can we get rid of this? And the first thing, and the first observation that we realize is that okay, actually almost all governing schemes has this kind of birthday bound one way or another. For example, for all protocols that are based on correlation robust hash function, they suffers from this bound because there's already this kind of gap in the correlation robust hash function. Okay, so those that use correlation robust hash function are kind of automatically ruled out because of this. If we use a AES to instantiate the correlation robust hash function, and those actually based on standard PRFs also suffers from this bound. Interestingly. For example, for the standard PRF based governing scheme, the proof usually works like this. Okay, so we kind of we have C hybrid. We'll see the number. We'll see is the circuit size, and in each of the hybrid, we reduce the security to the PRF gain, to the security of the PRF. So in each hybrid, we actually need a kind of a T over 2 to the n like a gap. Because we invoke the security of the PRF, and we need to do it for each gate. So that's kind of, it seems it's like a union bound across all the PRFs, but in the end that's what we can prove. Okay, it's like there's no matching. Actually, the interesting thing is that there's no matching bound on this kind of schemes. Sorry, there's no matching attacks on these kind of schemes, but the best provable bound is actually a birthday bound. So that's actually something interesting. It's like if somebody can actually come up with a way to analyze, or probably a way to fix it, that would be nice. Like so essentially the gap between what's provable and what's attackable. Okay, so over here. So if we actually use random oracle, then probably things are fine. Like we should be able to like prove something something beyond birthday bound security, because with kind of a fancy kind of primitives, we actually do not need C hybrid. We can actually swap. We can actually kind of just in one hybrid, swap all the gates from a real gate to kind of simulated gate in some way. That's actually already this is something that we already can do even using correlation robust hash function. So if you for those who are interested, you can actually take a look at the HalfGate proof. They were able to kind of swap all the gate in one hybrid. So that's how they can. That's why this bound is not even worse. If we do this and well, but there is a caveat. Okay, so in these slides, all of them are about what's provable. Okay, and as I said, what's provable doesn't mean that it's actually the security that we can achieve. It might be the case that there's no attack matching that bound, mostly just because, for example, the way that how we modularize all the construction. It is possible, for example, by using correlation robust hash, in Gobble circuit, we might be able to get better bound, because actually in the Gobble circuit, we are not using correlation robust hash as it is. Okay, so the adversary only has a very restricted. We are only using it in a very restricted way. In particular, for example, in the MMO attack that we mentioned previously, the attack actually requires input and output pairs to the oracle. And it turns out that in the Goblin scheme, we can never get this kind of pairs from the Goblin scheme. I'm going to talk about why this is the case in the next slide. In a few slides later, yeah. So well, but so we want to put a conclusion on this. So it turns out that actually there is an explicit attack. Okay, so essentially this is actually something we can do. Okay, so for the rest part, I'm going to first talk about the attack, and then talk about the fix, and then talk about the how the implementation can be done efficiently. Okay, so the attack is that we can show that actually the HalfGate scheme can be attacked with there's an explicit runnable attack on the HalfGate scheme with the birthday bound complexity. And then we show a new abstraction, a new instantiation that actually fix the scheme to make it actually almost with the bound that is almost optimal. And then we talk about implementation. So with this, like with the optimal bound, it actually comes with a slowdown in the computation. But we optimize enough. We optimize it enough such that we can still make like about 100 million calls per second for the hash function, and can gobble about like 24 million AND gate per second using this improved scheme. So it's I believe that the speed is almost enough for any like practical use, unless you if we use like correlation robots, we probably can get let's say like 30 million or something like that. But I don't think that that kind of difference actually makes sense given the like security that we can improve. So I'm going to make a very brief high-level overview about the HalfGate. Okay. So it looks a little bit complicated, but like for now, just believe me that like the relation, like all these formulas are correct. So what's important? It seems like a lot to like digest, but like so like, I guess let's like follow the notation like one step by one step. So in the so the HalfGate scheme is a scheme that is compatible with free XOR. Okay. So in free XOR kind of scheme, for each label we have a gobble label for zero corresponding for the zero wire. And the one wire, the label for corresponding for the one wire is essentially the zero wire XOR with a random free XOR global delta. So that's denoted by R. And that's also the case for the other wire. So if the gobbler wants to gobble a gate, so essentially the gobbler compute these two terms. Okay. So everything is well defined except this PB. So PB is just a random bit. This is a random color bit that we will use for point and permute. For now, just view it as a random bit is sufficient. Okay. On the evaluator side, we have the correctness of the gobbler scheme means that actually the correctness of the gobbler scheme means that actually evaluator will be able to get these two labels, okay. Labels corresponding to the actual value, but it looks random to the evaluator, so evaluator doesn't really know which label it is, but evaluator is able to get these two labels. Okay. So if we want to use the prior MMO attack, then essentially we want to get input-output queries to the oracle. Okay. If we get like input-output pairs from the oracle, then we can kind of find a way to launch the attack that we had previously. But it turns out that even if we can actually get one pairs of this kind of the oracle, then we can actually obtain R directly. Okay. So let me repeat again. So our goal was to obtain input-output pairs for the oracle such that we can break the scheme and get R. But it turns out that if we get just one pair, that's already sufficient for us to get R. It means that actually getting one pair of input-output pairs is as hard as getting R. Okay, so why that's the case? Let's say suppose that we have one pair of oracle of the oracle input-output. Let's say we have some WA and a hash of WA XOR R and I. So this is the input and this is the output of the oracle. Okay, why this is the output of the oracle? Because we have R over here. So this is essentially the oracle output of WA. Okay, so if we have this pair, then essentially it means that we can compare one of the term, and then the other term is going to be the output oracle output. Okay, these two terms are symmetric. Okay, so one of the term is always can be computable directly using hash, and the other term is essentially the oracle output. And if we have the oracle input output, essentially it means that we can strip out both of the terms, and then that leaves us with the PB times R. So we have if PB is 1, then we get R directly. So it means that actually, even if we have one pair, then we solve our problem. We complete our attack already. So this is not really a good way of the attack, because like it doesn't really reduce the problem to something easier. It's like it's an equivalently hard problem in some sense. Okay. Yeah. Okay, so that's not a feasible way. So what can we do? So essentially, what we do is that, okay, so we are going to obtain a pool of pairs. Okay, so all different kind of pairs, and some of them are probably valid pairs, and others are not valid. So this is something that we can still do. Okay, and then we are just going to use all these pairs in a way that we just use them as if that all of them are valid. To remind that this is so essentially now we are just going to focus on this single pair. So what we are going to do is that, okay, so we are going to compute HA equals to this times this. Okay. So essentially, like we are just going to strip off one of the terms. Okay. So if we strip off one of the terms, then the result of this computation is going to be a valid pair with 1/2 probability. And with 1/2 probability, it's just something that doesn't really like satisfy our relationship. But that's fine. We're going to treat all pairs as if everything is valid, and then run the attack that we had previously. Okay, we're just going to treat everything is fine, although we know that half of them are not actually valid, but we just run our attack. And if we get a candidate, it can be a candidate from the bad pair, it can be a candidate from the good pair. But that's fine. We are going to do a check to see whether this is indeed a good like R that we can get. And if it is not, then we're just going to restart. This is essentially like how we can extend the previous attack to this case. And it turns out that, okay, so if half of the pairs are valid, then actually the expected expected time of the expected running time of the attack is going to be doubled, because like there's a half probability that we actually encountered invalid people, and that gives us some candidate. So so if we spend more time, then essentially it's going to be fine. Okay. So I mean, if everything is on paper, it does not it's not that as persuasive as actually running it. So we actually run it. We actually implement it and run it. But we don't want to spend too much money on this, waiting for too many times. So we actually run it only for limited a small size and extrapolate for the larger size. Okay. So on the left hand side, we run it with two different kind of Gabor labels, label lengths, 40-bit and 48-bit. And then with different, then we will run it with different circuit size. Okay. So this is really just to verify that our analysis is correct. Okay. So the dotted line is our experiment in terms of how many queries that we need for the random permutation, and the dotted line is the analysis. So essentially, you can see actually that there's a small overhead from our analysis, but otherwise it's the trend is pretty much linear, that is consistent with our attack. And then we actually implement the actual attack and run it up to a garbled circuit of size with labels up to 64 bits. Okay, so with 64 bits, the running time is about slightly more than 1 million milliseconds. So that's can be run very fast, very fast. And if we have a 80-bit key, then the running time is about 2 to the power 40. It's I think if you extrapolate nicely, it's actually slightly less than 2 to the power 40, but that's fine. So what is 2 to the power 40? It's 2 to the power 40 milliseconds, right? So we divide it by 1,000. So that gives us second. Okay. And then this gives us minute. Then this gives us hours. And then divided by 24 divided by 30. So this is the number of months that we need to attack a garbled circuit implementation with 80-bit labels. That's about 400 months. Okay. And actually, so and the attack is highly parallelizable. So for this is something that we run on one machine, and this machine costs about $13 per month. Okay, so it's $13 per. It's kind of we customize the machine such that it's used as less resources as possible, and this instance actually costs about $13 per month. So attacking the whole 80-bit label is about 13 times 44. It's about 500. It's about $5,000 of cost. And let's say if we want to do it to be done in 1 month, we just launch 400 instances. Because I mean, anyway, in the end, just getting stuff. We just guess and guess. It doesn't really matter whether it is one machine or many machines. So it's highly parallelizable. Yeah. So it's actually a actual threat if we use 80 bits. It's something that can be actually concretely run using just some Google Cloud weak machines like this with one core. When we think about a fix in different ways, for example, what about can we just switch R? Let's say if we run 1,000 gate and we switch to a different delta, can that help? It turns out that it doesn't help at all. So the attack can be extended in a direct way, such that let's say if we have different circuit coupled with different people and send to the same adversary, the adversary can pull them all together and run one attack on all of them. And then with the same complexity, the adversary can break one of them. So essentially, like so this is still the probability that adversary can break one of them, and the C now is the sum of all circuit size. So essentially, it means that like changing delta doesn't really help at all. Okay, so this is so we need some way to we need some smarter way to fix it. Okay, it seems that I don't have much time, right? So the fix. So let's think about what kind of fix we can hope for. Can we hope for a collision robust hash function with optimal bound? In terms that it's not possible. So why? Because that would imply a random permutation, a construction from random permutation to PRF with a beyond birthday bound. And it turns out that this is not possible with one random permutation call. With one random permutation call, there was a recent result showing that the best we can do is n/2 bit of security. And with two random PRF call, with two random permutation call, we can get like something like 2/3 n bit. So this is not something we can do. Can we hope for a tweakable correlation robust hash function with optimal bound? Well, I mean, tweakable correlation actually implies like a correlation robust. So actually, like from random permutation, the argument is the same. And in the ideal cipher model, it seems very difficult with only one call for ideal cipher. It's like I don't know the answer. I don't know the definite answer, but it seems very, very, very difficult. And also, according to our symmetric key expert, it seems like very difficult. So whenever there's something difficult, when we make the thing easier, right? So we don't prove like a tweakable correlation robust. Instead, we prove a weaker version of tweakable correlation robust that is sufficient for most of the MPC usage. So essentially, the idea is that okay, so we have the tweak, but we are going to give an explicit bound on the tweak. So essentially, for example, we can say, okay, so we have the tweakable correlation robust, but the tweak will be reused for at most 2 times, for example. And this is already sufficient for gobbling and OT extension. So we impose a small tweak on the bound, and it turns out that and this is kind of the suitable level of weakness that we can use. It turns out that okay, with this kind of bounded query tweakable correlation robust, we can fix everything on back with the optimal bound. Essentially, now our construction looks like this. Okay, this E is the ideal cipher, and we have so now we have put the tweak as the key, and the rest part looks very similar to the MMO construction. Okay. So we can prove secure that if E is the ideal cipher, then actually the adversary's advantage is bounded by this. Okay. Actually, we can prove slightly better than this, but this is like a kind of simplification. So this U is the bound on the use of the tweak, and in practice, U is very small, like 2 or 3. And so here, see, we can actually have P plus Q instead of P times Q. So this is where we can get an optimal bound. Okay. I mean, if we want to support circularity, that's easy. Just like for any scheme over here, all the previous correlation robust scheme, just replace hash of X to hash of sigma of X, where sigma is something called a linear orthomorphism. So linear orthomorphism is something very popular in symmetric key. Essentially, it means that sigma, it's an orthomorphism if sigma of X is a permutation, and the sigma X of X is also a permutation. If both of them are permutation, then it's called an orthomorphism. It's a linear orthomorphism if this function is linear. So it turns out that if we just replace this by this, then we support the circularity directly. Okay. So how to find this? I'm going to talk about it later. Okay. So that's the fix. So essentially, the key message is that okay, we can just do this. And now in the multi-instance setting, the fix is also easy because we can actually also show that the previous scheme is secure even in the multi-instance setting as long as the bound is the same. Okay. So if we have the same bound, it doesn't really matter how many instances of this hash function keys are there. So we can actually bound them in the same way. So now the task is really just about bounding the tweak. Okay. In the multi-instance setting, it's like a balls and beans game. Okay. Think about it. So we have essentially every tweak is a bean. Then we have roughly 2 to the n beans. And we have like a circuit. We have many circuits of different sizes. Suppose that the maximum size is the sum of them is C. So essentially, we want to put C balls into all these kind of beans in some manner such that the maximum load is minimum. Okay. Well, the best way is that if we can maintain a global counter and just put them sequentially, that would be the best. Because in this case, U is 1, but it's essentially impossible because let's say, I mean, You gobble a circuit today, I gobble a circuit tomorrow, we may send to the same adversary. There's no way to kind of coordinate between all the gobblers. That's essentially not possible. Another way is that we can pick a random tweak for each gate. This one actually works great, but the problem is that if we want to pick a random tweak from each gate, then essentially it means that we need to generate more randomness. It means that we need more AES calls per gate to generate these tweaks. So it's also not an economic way to do it. So it turns out that a very good way is that we can just pick a random starting point for each circuit. Okay, whenever we gobble a circuit, we pick a random starting point, and then just increase our tweak monotonically from this random starting point. And then it turns out that everything just works fine. And concretely, let's say if we have 128-bit labels, that's another. And suppose that the average can get at most this number of gates, then the half-gate scheme can be proven secure with this bound. So like essentially it's about 125 bits of concrete security. That's like pretty nice. Okay. Some implementation. Let me just go through them very quickly. So the first part is the linear automorphism. So essentially, like instead of using doubling is kind of expensive. We actually can use some. We actually prove that this is also a linear automorphism, and this is kind of very like SSE AVX efficient, because we essentially just want to swap the higher 64-bit and the lower 64-bit and then do an XOR. So it's kind of very efficient. Okay. The second part is AES scheduling. So we use like the AES scheduling scheme from the optimization from a prior work that actually can like do key scheduling efficiently. The implementation of TMMO, essentially we can, it turns out that because the tweak is in the key, we can actually batch all key scheduling like as a batch of 8, because it's kind of predictable when we increase it monotonically. And it turns out that, okay, so with this kind of all the optimization, when we submit it, we can actually gobble about 15 million gate per second. And we recently improved it to 24 with more optimization. So everything is fine. Okay. So the implementation suggestion is that, so now, regardless of whether it's semi-honest or malicious, you should always use tweakable version, and you should always use the one with the ideal cipher, unless you have like many different customized reasons. And this will give optimal bound and a reasonably good speed. And we should always randomize the starting point of the tweak, so that like the balls and beans attack bound as hold. And I mean, but actually all these optimizations are pretty complicated. So we actually provide some sample code over here where you can use them directly. So they are pretty much self-contained. Okay. So the bring home message is that if we use remember that whenever we use 128 key, don't claim that the concrete security is 128 bit. Okay, this is actually very misleading. If we use 128 bit, don't claim 128 bit security. Don't claim it, then it's fine. If you claim it, then there can be problem. And always, and there is actually a way to get almost optimal security in many of these hash functions. Some take-home questions. So I guess there's no time for Q&A. So let me just leave some questions for you guys. For implementers, ask yourself what's the concrete security of your implementation. For protocol designers, ask what's the concrete security of your protocol. Are you distinguishing between this security and this security? And in the end, like when we get the concrete security, we actually model AES as the ideal cipher. And it's not clear, and in some sense, I mean, the best attack against the differentiating AES and ideal cipher can work up to 8 rounds. So it's not clear, but for the random permutation, it's 7 rounds. So it's not clear, like what are we losing over here? Okay. So we have a provable better bound, but does it really mean a better bound in practice? Because this two assumption has a difference, right? So, but it's not clear. So that's our question. Okay, thanks.
Thanks for the great talk, Xiao. Yeah, as you already said, we're a bit out of time for questions. Even though I still have to set up, so maybe there's time to sneak in 1 or 2. I think Peter has one.
Yeah, okay, so while Carsten's setting up, I was just wondering, you mentioned you had this lower bound on correlation robustness from a random permutation or general.
Using one random permutation.
Mm. Yeah. So does that still hold if you just have this weaker definition of correlation robustness, or is there a possibility to bypass it like that?
I'm not sure. I don't have that. I mean, that would be about whether random permutation, whether there's any construction from random permutation to weak random PRF. Yeah, I'm not sure actually. Yeah, that's a good question.
Sure. Yeah, that sounds interesting. Thanks for the nice talk.
Thanks.